did a fair amount of the operation that we have covered. You have the cross product of a vector with another vector. You have the curl of the vector. You have the gradient of a scalar. The dot product of two vectors. And this is the dot product of a vector with a tensor, which in turn is obtained from the gradient of a vector. Right? So now we looked at this term yesterday. So I want to, first of all, having seen that this is a vector identity, I look for the ith component of each and every term. Right? So the gradient of the dot product of A itself can be written as the ith component of aj, comma I. So this can be written as half aj, comma I plus ej, comma I. Maybe the two are equal, so I can write this as half times 2 times aj, comma I, and that will simply become. So I also pointed out that when you look at aj, this represents the sum of a1 squared, a plus a2 squared plus a3 squared, and you can simply replace it as aj squared. Interestingly though, if you do replace it, you will get the correct answer if you differentiate it. Differentiate aj squared, I get 2aj. Okay, so certainly you can get to a correct answer to a wrong method, but there is a contradiction here, because actually when I write this is aj squared, I am not implying any sum, because it's a particular component of a, the square of that. So when I differentiate it, clearly again there is no sum implied here over j. Right? So this is still not the correct answer. So you cannot say that I will forget that there is a sum over j here by writing it like this and then say that I am now summing over j. Right? So this is not correct. So whichever way you look at it, so you have to be careful when you write this. So this we have got. Now this one, what would be the ith component? This is like a dot a, right? So the ith component would be aj, ji. Right? So this would be aj, ai, comma j. So the right hand side becomes aj, comma I minus aj, comma j. Two behavior are not the same. Now we have to look at this, right? So I need the ith component of that. Right? So I can write this as a cross. And I can denote this as a cross b, where b is the curl of a. So the ith component of a cross b is epsilon ijk j bk. So now I need to write the kth component of the curl of a. How would you write that? Can you write it? Kth component. So that would be ek. Yeah, fine. Yes, fine. So now we have an expression for eijk, eklm. That's directly given in the assignment sheet. Yeah. AI, J equal to M.
I equals to M.
L, yeah.
J equals to M.
Yeah. Yeah, so it would be AJ comma I, the first term, which is what we have. It's very straightforward, given that we have already seen how to deal with this kind of a product. M and J equal to L. Yes, this is exactly what we have here. Right? We know how to handle these indices and the epsilons and so on. I think we have covered a fair number of operations. Are there any questions? So I'll let you work out some of the problems which we haven't solved. There will be other ways of doing this identity. So I'll let you do that. We will wind up assignment 1 and move on to the next topic. Before we go on to the next topic, I want to give an outline of the proof for the Cauchy's theorem. Right? We have already seen the Cauchy's theorem, which we haven't given because it's such an important result. I at least want to give a proof of just a sketch of our proof. Cauchy's theorem, what I mean is E of what we regard as Cauchy's theorem. But initially, what this is before we get to the stress tensor, the more explicit expression of the Cauchy's theorem. What this says is that at a given point, at a given instant of time, the stress vector, suppose I fix the time, and at a given point, and so I consider a surface passing through that point, orientation is N at that point. The N refers to the orientation of a surface, so I am considering a surface passing through that point. Orientation of a surface is defined at each point, and the curvature and so on to determine that. So that is the outward normal, unit outward normal, by which we identify the determine the orientation of the surface. Now, what the Cauchy stress theorem says is that at the same point, and of course at the same instant of time, I consider three planar elements whose outward normal are along the coordinate axis. One, two, and three. We consider three such orientations, and if I am able to determine the stress vector along those orientations, then the stress vector along an arbitrary orientation specified by the normal n is given by this equation. We then define the stress tensor using the components of these three vectors. That is the origin of the stress tensor. Right? This is what I have to prove. So what Cauchy actually considered, whatever point I will shift it to the origin, I will consider the coordinate system. All this 1, 2, and 3. Basically what Cauchy did apparently was to consider a volume element around the point of interest, which is in the form of a tetrahedron. The tetrahedron has 4 faces, which are each one of which is a triangle, and 3 of the faces Cauchy considered were along the 3 planes. So all this as C. It is not a regular tetrahedron. These distances need not be the same. So one face of the tetrahedron, if I call this is I'm calling this distance C, this distance A, this distance B. I call the points themselves as C, A, and B. how the tetrahedron is constructed. So one of the faces of the tetrahedron is OAC. The second phase we may consider is OCB. The third phase is OAB. The fourth phase is ABC. These are the four phases of the tetrahedron. Now suppose I consider OAC. So I am considering a volume element of fluid that has this structure. I am certainly free to consider any volume element along the point. Right? So I am sort of shifting this point to the orbit. I construct a coordinate system at that point. So I am going to look at the volume, a certain volume element which has a certain geometric form. You will see why the tetrahedron is chosen. Right? You can choose any arbitrary volume. The tetrahedron leads to Cauchy's results in a very simple manner. These are the four phases. So now, what is the outward unit normal for OAC? Unit normal for OAC minus E2. This is the normal, right? OBC outward, right? It would be minus E1. And OAB obviously would be minus E3. ABC, I will simply choose. So I will consider this in such a way that the ABC has the required orientation N. It's constructed so that one of the phases, that's the inclined phase. So of the four phases of the tetrahedron, three of them are along the planes, right? O13, O12, and O23. Those form three sides of the tetrahedron. The fourth side I will choose, the inclined one, to have the orientation that I am actually looking for. Right? So I can always choose it like that. Now, what Cauchy did effectively was apply the momentum balance to this particular body of fluid, which has the form of a tetrahedron. So we've already seen that that is the global form. I mean, not the local form, because the local form will involve the stress tensor, which we haven't yet proved. We showed that this can be written as integral equal to this area integral. So now, if you look at this area integral to actually complete the proof, we need something which is called, referred to as a mean value theorem of integration. Right? So I'll briefly explain that. So what the mean value theorem is, suppose I have an integral like this, very simple integral, moving away from that, and looking at a simple case in calculus, integral calculus, the integral of a function from A to B. So now we are going to argue, the basis of this argument is that all these integrals are bounded. Bounded means they have a lower bound and an upper bound, and they cannot grow up. That is the basic idea behind the proof. Now, suppose if this integral is bounded, right? Then there is we can put a bound that means the integral doesn't blow up, right? There is something called the mean value theorem. For instance, let us say the maximum shift doesn't go, let us assume. And it has a certain maximum value and a certain minimum value in this range, A to B. Certainly, I can place a lower bound and upper bound on the integral in the following way. Because the function has the minimum value at all points, then the integral would be given by small m times b minus a. And the function has the capital M at all points, suppose, that is the extreme case, that is not what I consider. Function has varying values over the range. If I take the maximum value of M, right, then if I assume some function which has the maximum value at all points, then its integral will be M, capital M times b minus a. Clearly, since f itself lies between M and M, small m and capital M, its integral will lie between these two limits. Right? That's very obvious. Right? So now what the mean value theorem says is that if the function is continuous, then the I can be written as f of psi times b minus a, where psi lies between a and b. So it is not, it lies between m times b minus a and m times b minus a. What would be its actual value? Right? It will be some value in between, but what the mean value theorem says for a continuous function that f will have some value at some point, let's say, between a and b. So at some point psi between a and b, the value of f at that point times b minus a will be the actual value of the integral. We don't know where that psi is actually, unless we carry out the integration. But it's certainly, there is some point psi between a and b, so that the integral can be written in this way. Right? So this is the basic idea that I am going to. This is often referred to as the mean value. This can be generalized to higher dimensions. For instance, if I have a to b, then again for a continuous function, we can say that this can be written as some f of psi eta times delta r. The delta r is the area of the region corresponding to the limits, the domain, area of the domain of the integration, something like that. There are theorems like this. So we are going to make use of that theorem because certainly it's there's nothing, from physical considerations we can say that all of these integrals have to be bounded. So what I am going to do is I am now going to apply the mean value theorem first for this integral. That's very easy to do. So I will write this as some k times delta d, where k, if I want to strictly interpret the mean value theorem, is some value of the integrand, right, within the tetrahedron times the volume of the tetrahedron. That there are expressions for the volume of the tetrahedron, but I don't need it here. I will just consider delta V as the volume of the tetrahedron. Right? So I can write the left hand side like that. So I am not here worried about calculating these integrals, but I want to prove which relates on the mean value theorem. Now you look at this integral, right? So this is over the surface, bounding the volume. So there are 4 planar surfaces. So on each plane surface, the normal is the same at every point, right? For the same way, for all points on this plane, the normal is along minus E2, right? So if I have to, because the integral not not only depends on x and t, it also depends on the normal. But since if it is a curved surface, I have to evaluate it at each and every point. Then the normal will be varying. Here, there are 4 parts of the surface that I have to consider separately. Right? So, I can write for all of them, the normal, for each one of the 4 surfaces, the normal is the same at every point. So, I can write this whole integral as for area 1. So, I now call this OBC, area OBC, I call this delta A1. Of course, delta A1 is very easy to determine. It will be half times B times C. But I don't need those expressions here. Area OAC, I will call this as delta A2. Area OAB, I will call this delta A3. And area ABC, call it as delta A. Right? I give those. So now, by applying the mean value theorem, let us say on OBC, right? So I will get T some theta 1, right? X, because that's the mean value, some point on the face OBC, T minus E1 times delta E1. Now apply the mean value theorem. What the mean value theorem says is that, right, this is our 2-dimensional, right? Of course, this area is in the 3-dimensional space, but what it says is that depending on the nature of the integral, if this is 1-dimensional integral, there's some value of the function at some point in that interval, right, multiplied by the length of the interval, right? For the 2-dimensional, it is the area of the region, the domain of integration. So clearly, the domain of integration here is OBC, right? So I will get the eta 1 is some point on OBC plus eta 2 is some point on, just make sure that eta 2 is some point on OAC plus, these are all vectors, right? So plus, I call this simply eta. The eta is an element A, B, C minus, this is not minus, this is simply n times delta A. This is what I have. So I applied the mean value theorem of integrating with each and every face of the tetrahedron and calculated the integrals. So now, it's possible to show, then we need to do something about the geometry of the tetrahedron. It's possible to show that actually delta A1 is equal to N1 times delta A. Delta A2 is equal to N2 times delta A. Delta A3 possible to prove that. We see how to prove that short. So what I am going to now do is replace this as N1 times delta A. This would be N2 times delta A. This would be N3 times delta A. Now this delta B can also be written as some factor times delta A, right? So I will now write this as some K prime C. The C is the height of OC times delta A. So I can write that out. So I am absorbing all the constant factors into this K and calling it some K prime. So the volume can be written as C times delta A. There will be some other factors, right? So I am absorbing that here. So now what I do is I simply divide by the delta A is going to cancel, right? So I can divide throughout by delta A. Then I take the limit as C goes to 0. If I take the limit as C goes to 0, then I will get, what will I get? So I will get the entire right hand side will be 0. So I will get E. So now what happens to eta 1, eta 2, eta 3? What is this whole procedure amounts to? When I make C tend to 0, all I am doing, because I am finding what I want is a local relation. This is at a given point, but I have constructed a volume around that point. I have applied the momentum balance for the body as a whole, and clearly now I am collapsing that body to the point. So when I am talking about C going to 0, that means that it is not just that C becomes 0 and everything else remains the same. But at every point I am keeping the form of the tetrahedron intact. So when I start like this, now the next element I will get something like this, right? That will be ABC. So I am now collapsing it to a point, right? That is the point at which I want the relation. So what I will get is effectively almost got the vessel. This is one step left. In this limiting process, when I make C 0, because this is dependent on the volume, it is going to reduce to 0. Each one of those will have the same form, but because n1 is not changing, that's what you have to understand, right? The structure of the tetrahedron is the same, so the normals are remaining the same, but the tetrahedron is shrinking to a point. We are retaining the shape of the tetrahedron as we carry out this limiting process. So each one of these points will collapse to the point that I want. The normals are remaining the same because the orientation of each of the faces remains the same, right? So finally I get this result at that point, right? They are not yet done because I have this minus E1, minus E2, minus E3. So to determine them in terms of E1, E2 and E3, I now consider the following special cases of n, right? So I consider n is 1 such that n1 equal to 1. This is somewhat tricky, I think it's difficult to explain, but in terms of the algebra, it's quite easy to see. So what Serin points out that this whole proof, the way it is constructed, is valid for n greater than 0, n1, n2 and n3 greater than 0. But by applying a principle of continuity, I can make the whole procedure valid for n1, n2 or n3 equal to 0 also. So I am allowed to consider this possibility. If I just substitute this, right, what will happen? I'm sorry, this is n1, n3. And that is important. So I left that out. So now we have put n1 equal to 1, n2 equal to 0, n3 equal to 0. So this will go. n1 is equal to 1. So d of x what? This particular case, what does this imply? N is equal to the vector n is equal to
E1.
is equal to
E1.
E1. So what this means is that E of x E minus E1 is minus of E of xt E1. So we see the meaning of this shortly. This is often interpreted as the generalization of Newton's third law to a continuum. So from that, from the same procedure, by now considering case 2 would be n1 equal to 0, n2 equal to 1, and n3 equal to 0, which is n equal to e2. I will get ext minus e2 is equal to minus e of x e2. And similarly, third case would lead to so what we get finally is E of x E n is equal to minus n1 T of xt minus E1 by taking it to the other side, right? So that would be n1 T of x E1 plus n2 proved it. Maybe not our steps may have been very clear. I don't think I've explained it that clearly, but still to get a rough idea of the proof, exact each and every step, the technical point, you won't even go and read up in Aris, but even there are some points you cannot, I think, explain very clearly. But this is roughly the idea behind the proof. Right? So this is the standard procedure we have seen, even to get the local equation of motion, we formulate a balance for the body as a whole and then reduce it to a point. That's exactly what Cauchy did. But he assumed a special form of the body, the form of a tetrahedron, right? So as to obtain the result that he finally obtained. Of course, you can ask, well, is the whole result dependent on considering a tetrahedron? What is so special about it? Simply was a device used by Cauchy to arrive at the result. Later authors have generalized the proof, not really dependent on a particular geometry and collapsing it. But that proof would be even more technical and difficult to comprehend. So we don't really need to go into it. Roughly, this is the idea behind the proof. Are there any questions? Yeah. Exactly. That's true. So we are applying. Eta, that is eta 1, that is what the mean value theorem says. The mean value theorem says is that, for example, if you have an area integral, and what it says that this integral, for instance, right, has 4 parts. So for part 1, which is delta A1, so I am considering the integration over this. So obviously the normal is the same at all points on that surface, right? But however, the points themselves, there are infinite number of points. This is the region, right? So I have to carry out strictly this integral over each and every, consider the whole domain. So because t will depend on each and every point. However, the integral itself can be written as the value of t at some point in the region times the area of the region. That is what the mean value theorem says. So eta 1, the vector, is some position vector or the position vector corresponding to some point on the face OBC. If you are not clear about how this came about, that is just the mean value theorem applied to that area. Right? So we assume here continuity and all those are taken care of. So the function is continuous, as I pointed out. Consider the simplest is to consider one dimension. So what it says is that for one dimensional, right, integral a to b f of x dx can be written as b minus a, which is the length of the integral, times the value of the function at some point within the integral. The same way for two-dimensional, it would be the value of the function at any point within the domain. Here there are two values, x and y, times the area of the domain of integration, and so on. The same for three-dimensional that I have applied here. A is just some value of the integral at some point within the tetrahedron. That's all. Any other questions? Yes. We'll come to that. Yeah, we can prove that. First of all, this is very important because not just for this proof, right? In general, if you want to know how to calculate the normal, this will become very important as we go along to any arbitrary surface. Right? So I leave that as an exercise to give a pointer to the proof of that. So delta A1, we know the expressions. So yes, you can complete that question. Delta A1 is clearly half times, right? Where is A1? Delta A1 is area OBC, half times B times C. Delta A2 is area OAC, so that will be half times A times C. Delta A3 is half times A times B. I will let you get an expression for the area of ABC. What is delta A equal to? I am not going to do that. You should know how to find the area of a triangle. Three sides are known of ABC. You should somehow be able to get it. Right? And they are all hypotenuses of the right angle triangle. So you can easily find out. Or you have to calculate some angles and you can use your standard formula for the area of a triangle and find it. What about the normal? Normals for three of the faces is very easy to see. Now the normal for the fourth face, how do you find the normal to any surface? I give you one method, right? One method would be, suppose a very general way of expressing the equation of a surface in three-dimensional space, x1, x2 and x3, is this. So suppose I am having the equation of a surface represented in this way, then it can be shown that the normal, the unit normal, I'm not talking about the unit vector, unit normal is given by the gradient of f divided by the length of the gradient of f, that I call as a norm of the gradient of f. We have to calculate the gradient, we know how to calculate df by dx1, df by dx2, df by dx3. So this is basically df by dx1 d1. That would give the direction of the normal. Of course, I have to divide it. That would be df by dx1 whole square root of the length. Right? If I do that, certainly you must have known in your mathematical method how to make the length of a vector unity. You just have to divide the vector by its length. That's all. Right? So this is what it is. So all find the equation of the plane ABC. The plane ABC. What is the equation of the plane? How would you go about finding the equation of the plane ABC?
X by a plus y by b equal to 1.
One simple way is you can just infer it by inspection. But if we are not sure, right, to find the equation of a straight line in two-dimensional plane, we know how to do it. I need 2 points on the line. Then I can find the equation of the line. There's different ways of representing. Clearly, the equation of a line whose intercepts, x and y intercepts are a and b, is given by this. So now the equation of the plane would have an additional term, z over c, right? We don't know actually, if you are not sure, the general equation of a plane can be written as alpha x plus beta y, I'm sorry, x1. Equal to 1. I need only 3 parameters to determine the equation of a plane. So you can easily verify that it will reduce to this here, in this case, where the O1 intercept is A, O2 intercept is B, and O3 intercept is C. Right? All I have to do is 3 points I have to substitute. Right? So what are the 3 points on this plane? One is A, 0, 0. Another is 0, B, 0. 0, 0, C. Certainly they satisfy this. By inspection you can write it, but if you are not sure, when just give us some other arbitrary plane, I need 3 points on the plane, I can find the equation of the plane. Right? This is just like some y equal to mx plus c, a straight line in 2 dimensions. 3 dimensions for a plane, you have an additional coordinate. Right? So that is what this is. Now this is already in this form. This is already in this form. So what is df by dx1? So what is the normal? 1 by a e1 plus 1 by b e2 plus 1 by c e3 divided by square root of 1 by a squared plus 1 by b squared plus 1 by c squared. That is the unit normally for this plane. Right? So we have found what is n. So n1 is clearly 1 over a by square root of 1 over a squared plus 1 over b squared plus 1 over c squared. So we have now part of the proof for us how to prove that delta a1 equal to n1. So n1, n2 and n3 I have found to verify, right, whether delta a1 is equal to n1 delta a and delta a2 equal to n2 delta a. We need a formula for delta a. You can infer what that formula is because these equations are correct. But if you want to prove it, you need an independent expression for delta a, that is the area of the face ABC. Then you can verify these relations. And so we have run out of time. Are there any quick questions? Yes, you had a question. Yeah, and I'm collapsing. So I'm shrinking the tetrahedron. So everything collapses to that point. That's a limit. You have to imagine that. So there no the tetrahedron right up to the last moment is a tetrahedron. Right? At that limit, it collapses to a point. So this is something about the limit that you just have to infer. Right? That's how it ends at the point. origin, which is x. I said I want everything at x. So I'm constructing this whole thing around the point I want the relation. So convenience, I have sort of shifted this and considered that as the origin. So I'm constructing a coordinate system around the point x. So I'm calling that as the origin. And so this whole thing you can imagine constructed at whatever point I want the Cauchy's relation. Right? And then I'm collapsing everything to that point. Any other questions? Okay, we've run out of